We're moving into the next section in our book. Yet another use of the double integration, and it has to do with measuring the area of a surface. So the book has a more formal derivation walkthrough that shows notationally, how something is built from scratch, and it ends in a formula. My hope is to kind of bridge their book's information with the formula and provide a little bit of insight into how it works. I am not going to fully write out every detail from the book. You have a book. You can do that. I want to sort of explain some of the pieces. So ultimately what's going to happen is we're going to have our surface area that will be equal to a double integration over a region in the XY plane. And the shorthand notation for this is ds, and the S is capitalized. And this stands for surface. In our last chapter, we'll find that this is a foundation for what's called a surface integral. We have to learn how to measure the surface itself before we can add any interesting details. But let's just look at this visual example. So this dome, which we actually have a possible equation for this. It could actually be the graph of z equals perhaps 4 minus y squared. This was called a cylinder, as I like to describe it, a two-dimensional shape that extended into the third dimension forever. And what we're interested in is the fact that it makes a surface. It does extend below the XY plane. What we're going to do is we're going to just look at what if we were to focus our energy on the part of this graph that resides over the rectangle in the XY plane. So the rectangle down here becomes our region of integration. But then the surface is this shape in 3 dimensions here. That's what the capital S is referring to. So ultimately, this is going to become a formula that is befitting a double integral. And we're going to, again, highlight some of the key aspects of what would be the book's formal derivation. All right, quick little review. If you take 2 vectors and you perform the cross product operation, you build a vector that is orthogonal to the original 2 vectors, or we would say perpendicular if they were touching, perpendicular to u and perpendicular to v, extending the 3rd dimension. But if I then were to find the magnitude of this vector, I would actually be generating the area of this parallelogram. So these are all earlier aspects about vectors that we've seen before. Proving this is equal to area is a rather interesting trigonometry and algebra experience, but the calculation is true. So I want you to think of this parallelogram. Now, I want you to think of many of these parallelograms. If we were to go back to our surface here, let's suppose I were to take this surface and break it into many parallelogram portions, remember what the double integral does is it adds up infinitely many, infinitely small quantities. And it turns out that it's going to sum the area of all these parallelograms. I will not attempt to draw more, and the book doesn't really do that either. Our book, at least, doesn't. Back to here again. Through the book, you find out that this U cross V vector experience becomes the vector the negative of the x partial derivative and the negative of the y partial derivative in 1. There is a huge derivation to get to this point at a particular location. But I want you to think of the x and y derivatives as sort of your dimensions for these little parallelograms. The x partial derivative measures the change this way, and the y partial derivative measures the change that way. And then there's your change in z. And then the magnitude of this vector is the area of the parallelogram. And 1 squared is 1. If you square this, and if you square this, again, I've extremely oversimplified a few algebra steps, but the concept is we build these infinitely many parallelograms to, it's one way of describing this in art would be a mosaic. Many small tiles assembled together to form a surface. This would be the area of just one of these small parallelograms. Well, it turns out the surface area formula will sum this total one squared is 1, the x partial derivative squared, and the y partial derivative squared. And if you were to go back to Calc 1 or 2, you would see this is very similar to arc length formula. This is going to be our method for calculating the area of that surface there. Later in the next, well, not too far down the road, we will actually add other interesting pieces like density functions, and we'll be able to find the mass of this surface. But that's for later, not for now.